Hey, what's up, guys? This is Sheng here. So today let's take a look at this one, 1696 jump game number 6. So you're given like a zero index integer arrays, generate nums, and an integer k. So you can do a move, a jump, right? So which means that you start from index 0, and your goal is to reach the end of the array, which is the n minus 1 index. And you can only jump forward at most k steps, which means that you can jump from 1 uh, from 1 to k at most, and you need to return the maximum score you can get. So the score is a summary of all the number of all the indexes you have ever visited. So for example, this one you have like 1 minus 1, and the step you can jump is 2. So which means that you can at most jump 2 numbers. So and in the example one here, so the optimal uh, solution is you start from 1, and then you jump from 1 to minus 1, and then from minus 1 you jump to 4, and then from 4 you jump to 3. That's why the answer is 7. And similar for this one, right? For now, example 2 here, you jump from 10 to 4, since you can skip 2 numbers. Basically, you can jump 3 steps, right? And then from 4 to 3. That's why the answer is 17. Yeah, so on and so forth. And here's the constraints, right? So the constraint is 10 to the power of 5. So this gives us like a hint what kind of uh, solutions we can choose from. And I think it's not that hard to figure out. This is kind of like a DP problem, you know. So I think the DP transition function is pretty straightforward, right? So it's like the DPI, right? The DPI means DPI means that from 0, and the ending the ending point is the ice uh, numbers. What is the maximum score I can get? Right. So I think the state transition function is pretty straightforward. So basically, we just need to get the maximum, right? The maximum from all the uh, all the DPs, right? The DPs from uh, from I minus k minus 1 to I minus 1. Yeah, this minus I think this one is plus k. So I mean, you guys get the idea, right? And then plus nums plus the card number, right? So it means that so we have these numbers here, right? I mean let's say we are at this number here, right? This is the I, and let's say the k equals to 2. So it means that uh, when we if we want to stop at this location, right? So we can only jump from how many place we can, how many options we have to jump to the current location. We have if k is equal to 2, we can jump from here. So here is 1, and then we can jump from here. So there's only these 2 options we can choose from, because here is out of the range, right? So here, from here to here, actually that's step 3, right? And yeah, so basically that's the state transition function. Basically, we just at each of the I here, we just need to go through all the previously DP within the range of the I minus 1 here, right? This I minus 1, and then from I minus 1 to I minus k plus 1. Yeah, and then we just plus the numbers, and in the end, we simply return the dp n minus 1. That's going to be our answer. But the time complexity for this naive dp approach is like n squared, right? Because for each of the I here, we're gonna loop through k numbers of dp's, and the k can also be as big as the number itself, the length itself. So that's why it's an n squared solutions, and it will TLE. So which means that we have to find mm, a better way to solve this, right? And so here we're getting the maximum of some values here, right? And actually this is like a big hint, right? And and here actually the problem can be converted into a maximum value for a sliding window, right? And here, since k is equal to 2, that's why the sliding window size is what? It's 2 plus 1. It's 3, because we are including the current one, right? So, and the size of the sliding window, even when the k is equals to 2, is 3. So we just need to find a more efficient way to give us the biggest, the maximum values, right, within the sliding window. And to do that, I mean, I think some of you may have already known, right? So we have two options, right? So first one is the priority queue. Second one, and the priority queue is an n log n solution. And there's even a better way to do it, which is by using to use the monotonic queue, which will give us log n time complexity. I mean, in total, which is basically here will be a O1, but we have a ON in total. If it's a priority queue, it will be a log n time complexity for a priority queue. I mean, you can use either way, but since we know there's the better options, that's why not just use that. So I'm just going to use the monotonic queue to maintain the maximum value within the sliding window. And actually, so to be more specific, to get the maximum values, we need to use a decreasing queue. So, and similar, if we want to maintain the smallest numbers in the sliding window, we use the increasing queue. Because when we have like a decreasing queue here, we can use, I mean, the decreasing queue of 0, that will always give us the maximum values for the current sliding window, which will only take O1 time. Yeah. So let's try to implement this then. All right. So we have n equals to a length of the nums. That's gonna be the total length, and then we have a dp, right? So the dp is since we're getting the maximum, I'm initializing everything with the negative big negative numbers here. So the n here, and then we have a dp 0, right? So the 0 is nums 0. That's the base case. Mm, yeah, because here I don't think we need like n plus 1 size here. We can just use n size, because we can just get the values for dp zeros, and then when we start the loops here, right, we can just start from 1. Because if there's only one numbers, right, actually the starting point is the ending point, which means that there will be only one numbers we ever visited, which is the number itself. That's why the dp0 will be the number itself, the number 0, right? And then here we have and in the end, like, we just need to return the dp minus 1, which is the last one. Okay. So, and now we need to also define decreasing queue, which will be used to store the maximum dp value within the sliding window. And actually, the way this decreasing the monotonic queue for work is that instead of storing the number itself, we'll be storing the index, because there could be a duplicated numbers, right, on different indexes. That's why we have to use an index, so that we can uh, do the pop and append correctly. And so for DP zeros, since we're starting from 1 here, right? I mean, at the beginning, the DQ will have like index 0. Okay, that's gonna be the basically the biggest numbers we have when we have like only one numbers. And now, and we have we need to maintain this monotonic, the sliding window. So actually, this I spent some time to troubleshoot. I was using the K because I didn't notice that actually to jump K, actually the size of the sliding window is K plus one. So and I'm just going to use this one here, K plus one, the size, right? The size of the sliding window, and now we can use the K. So this how this thing works is that first with a new I here we check if there's any numbers that we need to move out of the sliding window. So basically if the I is equal greater than K, right? And then we know that so the numbers on the leftmost needs to be moved out of the sliding window. But since we are only maintaining certain numbers in this decreasing queue here, that's why we also need to add a second conditions here, right? So if the current biggest number, right? So if the current biggest index, the number index is the I minus k, then we just do a decreasing q dot pop left, right? So the reason we add this one is otherwise, if the one that gets moved out of the sliding window is not the biggest one, then we don't have to do anything for this decreasing q. We only do this when the ones gets moved out of the sliding window, it happens to be the current biggest one. That's why we need to remove that one because that will affect our calculation. Okay. Okay, so that's that. And now we have what do we have? We have like we have a sliding window, right? We have a valid sliding window, and then we can just use it to calculate the current DP, which is DPI equals to nums I plus the DP of decreasing Q 0, right? Because this is the biggest DP values we have, right? And okay, now the next step is to update the sliding window. Sorry, to update the decreasing Q, basically to maintain this monotonic Q. So while Q is not empty and the DP of the decreasing Q of -1, if the top one, the DP values, is either equal or smaller than the DP of I here, right? And then we need to pop this thing out. And then in the end, we just append the current index to this decreasing queue. Yeah, so I mean, so this is, this is pretty, I think it's not hard to understand, right? So with the reason we're doing this while loop here is because, we're maintaining like a decreasing DP values in this decreasing monotonic queue here. Uh, so that, right, so that we can use O1 time, sorry, so that we can use O1 time to get the biggest values. And and here since even though we're having a while loop here, right? And because each numbers or each DP will be pushed and then popped from this decreasing queue only once. Which makes this while loop also a O1 time complexity. Sorry, ON time complexity in total. Basically, this one will not add another level of time complexity on top of this ON here. Yeah, and yeah, I think that's it is. And if I run the code here to accept it, right, and I submit, yeah, so it's pretty fast, right? So the reason being is that the time complexity for this solution is O of n. Like I said, the only thing we need to care is this for loop here, and the while loop here it's not it's like in total is 2n. So basically the O of n plus O of 2n, I think. Yeah, this adds a append and pop. So in total it's still a O of n time complexity. Yep, I think that's it for this problem. I think it's a pretty standard. It's a very standard DP problem, just with a little bit of optimizations because of this 10 to the power of 5 constraints. And the way I'm using is to use the monotonic queue because that will give that has the mm, best time complexity. And some other options is that you can also use the priority queue, right? I won't implement that, but it should be pretty straightforward to use priority queue. Basically, priority queue is also being used um, to uh, to maintain the maximum number within a sliding window. I think that's that, and I think there's also you can even use the segment tree to solve this problem, but that's a little bit more complicated to implement. I will not go over that at the moment. Yeah, I think that's it. Thank you so much for you guys to watch this video and stay tuned. See you guys soon. Bye bye.